Hello, everyone. My name is Marley Wies, and my project is on the extraction of cellulose nanocrystals via sulfuric acid hydrolysis from post-consumer cotton elastane textile blends with elastane recovery. 92 million tons of textile waste was generated in 2017 globally, and this number is only increasing. In the US, 85% of textile waste is landfilled or incinerated, both of which release toxic gases that harm surrounding communities and the environment. Even if textile production were to stop today, we would still face the challenge of managing the vast amount of existing textile waste. To effectively address this and promote a circular economy, my research focuses on upcycling, where discarded textiles are transformed into high-value materials. Cotton is a widely used fiber, composed of over 90% cellulose, a natural structural polymer in plant cell walls. In nanocellulose extraction, sulfuric acid hydrolysis breaks down the amorphous regions of cellulose while preserving its highly crystalline structure. The result is rod-shaped cellulose nanocrystals, or CNCs, as shown in the STEM image on the bottom right. For perspective, a nanometer is roughly 1/1,000,000th the thickness of an American dime. Sulfuric acid hydrolysis also introduces sulfate half-ester groups, circled in red, to the cellulose chain, which helps disperse the CNCs in water, making them easier to apply industrially. CNCs are biodegradable and highly versatile. Notably, they can serve as a sustainable alternative to microplastics in cosmetics and personal care products, addressing a growing environmental and health concern. While CNC production is still emerging, a few facilities demonstrate its large-scale potential using sulfuric acid hydrolysis, the same method applied in my research. A recently built commercial facility can produce 300 metric tons per year. Since CNCs are used in small quantities to enhance materials, this capacity goes a long way in industrial applications. These facilities show that large-scale CNC production is feasible. It just needs adjustments to work with post-consumer cotton, unlocking a new source for sustainable nanomaterials. Previous research has examined CNC extraction from pure cotton and cotton blended with polyester or acrylic. My research takes this a step further by considering another complication, cotton elastane blends. Elastane, also known as spandex, can stretch 4 to 8 times its length and is added to other fabrics in small amounts. The SEM image I took shows the surface details of elastane close up. At the end of its life, unfortunately, the material's stretchiness can make it difficult to recycle because it tangles in machinery during the shredding stage of traditional recycling methods. Thus, the cotton that is blended with elastane is left non-recyclable. My research aims to address this recycling challenge, along with the gap in research, by developing a scalable upcycling process for cotton elastane blends that extracts nanocellulose and recovers elastane fibers. In my research, I also analyzed CNC properties and yield. A post-consumer cotton elastane garment was donated for this research. Before proceeding with the extraction of CNCs, I wanted to determine the content of the garment. To do this, I separated the cotton from elastane using dimethylacetamide, or DMAC, to selectively dissolve the elastane. I collected the insoluble cotton and found the fabric composition, including and excluding moisture content. On average, the fabric was about 94% cotton and 6% elastane, which closely mirrored product labeling. I took FTIR spectra of the fabric before and after separation to see the different components. The x-axis shows the wave number and the y-axis is the percent transmission. As expected, the initial fabric appears as cotton because it is predominantly cotton. To get the spectra of the elastane, I placed the solution of elastane and DMAC on the FTIR, allowed the DMAC to evaporate, and which left the elastane behind for analysis. To confirm that the two components were actually cotton and elastane, I compared them with an FTIR library. We can see some of the characteristic peaks of both fibers. For instance, elastane contains nitrogen, so there are peaks that show nitrogen-hydrogen stretching and bending. Here are SEM images I took of the fabric before and after the separation process. On the left, elastane fibers are more randomly oriented, crossing and weaving between the cotton fibers to provide stretch to the garment. On the right, the ribbon-like structure of cotton fibers are more clear after the removal of elastane. EDS analysis shows that before the separation, there is carbon, nitrogen, and oxygen, with the nitrogen indicating the presence of elastane. After separation, the sample contains carbon and oxygen, but no nitrogen, confirming that all the elastane was successfully separated from the cotton. Sulfuric acid hydrolysis has shown to be effective for pure cotton and other cotton blends. It begins with a simple pretreatment to gently clean and increase surface area. Then the fabric is placed in sulfuric acid with optimized parameters. Quenching with cold water stops the reaction, and next there are steps to neutralize the excess acid and purify the CNCs. The result is a suspension of CNCs in water. This served as the basis of my upcycling pathway. I needed to experiment with different approaches to separate and recover the elastane components. The first method I tested followed the approach used by Wies et al. For cotton polyester and cotton acrylic blends. In this case, both the cotton and elastane were placed into the sulfuric acid and separated before subsequent neutralization and purification. In the second method, I separated the cotton from elastane in DMAC before subjecting only the cotton to sulfuric acid hydrolysis. Next, I compared the resulting CNCs and elastane recovery. When I separated after hydrolysis, there was no recoverable elastane. EDS analysis of the final CNCs showed trace amounts of nitrogen, indicating that a fraction of the elastane fibers contaminated the CNC suspension. Unlike polyester and acrylic, elastane becomes very degraded in sulfuric acid. For the method with separation before hydrolysis, however, I separated the elastane and DMAC solution to recover both the elastane and DMAC. The elastane was suitable for further recycling, and the DMAC was reusable for future cotton elastane separation. DMAC recovery is important because it drastically reduces cost and mitigates environmental impact. I looked at the FTIR spectra of the final CNCs and compared them to quality CNCs produced from pure cotton and cotton blends in Ruiz et al. Both methods from my experiment had the signature peaks of CNCs. I used dynamic light scattering, or DLS, to compare the sizes of CNCs obtained from both methods. DLS provides a Gaussian distribution with the x-axis representing hydrodynamic diameter and the y-axis indicating relative amount. The CNC sizes from the two methods were similar, measuring 51.1 and 60.1 nanometers each. Notably, the CNCs from the method involving separation before hydrolysis fell within the size range of high-quality CNCs produced by the USDA Forest Products Laboratory pilot plant. CNC yield is the grams of CNC produced per gram of original cotton. Usually, researchers freeze-dry CNC suspensions to measure the CNC mass. However, the vacuum pump on my freeze dryer broke on its first use, so I had to devise a creative approach. I started with purchasing quality purified CNCs. I made a 10 gram per liter solution and serial dilutions from there to create calibration standards. For each of these, I placed 5 microliters on the FTIR and dried the water. Here are the FTIR spectra of these calibration standards with their corresponding peak areas from 850 to 1500 wave number. As the concentration of the calibration standard increases, so does the peak area. By plotting the concentration of CNCs on the x-axis versus the peak area on the y, I created this calibration curve. With well-fit linear regression, I had a way to convert peak area from my unknowns to their respective CNC concentrations. For instance, the area of 14,502 corresponded to the concentration of 11.9 grams per liter, and the area of 6,255 to 5.03 grams per liter. Those represented yields of 50.7 and 55.3 each. This evidence supports the conclusion that the separation of cotton and elastane before sulfuric acid hydrolysis is better than the other method when considering the yield of CNCs. Based on the comparisons I made, here's the upcycling pathway that I propose for cotton elastane blends. The fibers are separated before hydrolysis, and the elastane and DMAC are recovered. The final CNCs exhibit improved yield and are nanoscale. My research pairs economic opportunity with environmental benefits by expanding the scope of nanocellulose extraction to cotton elastane blends, a waste stream previously considered unrecyclable. Cotton waste is prevented from entering landfills or incinerators, which avoids high disposal fees, environmental harm, and health risks. Synthetics, like elastane, are successfully removed and suitable for further recycling, and CNCs have high value with applications in diverse industries. Considering the current capacity of a CNC commercial plant, my pathway could save 1,880 kilograms of cotton elastane waste per day, which is equivalent to around 11,000 t-shirts. In the future, I'd like to continue expanding the scope of CNC production to post-consumer cotton polyester elastane blends. I'd like to thank JSHS for the opportunity to share my research, as well as my research mentor and my parents for their continued support. Thank you so much for listening, and I'd be happy to answer any questions.